I'm not really a bearing connoisseur, but this bearing spacer, I don't think it's up to the job. So I have this friend, he asked me if I could make him a couple of spacers for a wheel bearing, for a car he's rebuilding. He sent me a few pictures and a sketch, because we don't live close to each other, so I had a look at the sketch and... yeah, sure, how hard can it be? In case you aren't familiar with bearing spacers, which should not be confused with wheel spacers, they fit between two bearings. In the case of my friends, single row deep groove ball bearings. A spacer like this should only make contact with the inner races of the bearings, and its job is to help establish the correct initial setting for the bearing set. OD and ID are not critical dimensions. What's critical is the length. Take this small hub I just printed as an example, and let's see what happens as I change the length of the spacer. If I use a spacer that's too short, or no spacer at all, I'll be basically driving the inner races against each other as I tighten the hub nut. That's called preloading. In this case, preloading the inner races. Bearings, in their free state, have some internal clearance, both axial and radial. By pushing on their inner races, we are effectively offsetting the races and forcing the balls to run against the sides of the raceways. That offset of the races is what allows for this preload. It takes up that internal axial clearance, which makes the bearing more rigid and less prone to suffer from vibration. That also helps reducing the ball skidding effect. So if a bearing is correctly preloaded, it should last longer. I don't know if you ever looked for play between the races of a bearing. A few years ago I remember looking at a new bearing and thinking, this can't be right, how can a new bearing have this kind of play? Turns out it was this axial play. By the time the bearing is preloaded, it should be gone. And the spacer is there to act as a stop and make sure we don't ruin the bearing. Because if we overdo it, the running friction will be very high. The bearings will overheat and chances are they'll be toasted in the short term. But while axial play is relatively easy to feel and see in some cases, radial play might not be as easy. However, it must exist to account for changes in the bearing dimensions. For example, if we press fit the bearing in some housing or a shaft through the inner race, we're essentially deforming those races, even if just a little. That actually takes some of the bearing initial radial play. And when the bearing is under load, in operation, heat will make the races expand, and there goes some more of that radial play. The rest can be taken axially by preloading. Ideally, under operating conditions, we should have no internal clearance for optimal bearing life. So when you replace bearings with spacers, if they start getting stiff as you tighten the nut, remember to stop and measure the spacer. Compare it to the distance between the outer race's shoulders. It should be the same. Never assume that old spacer that you have will be fine for the new set of bearings, and certainly don't mix new and old stuff without proper measuring. Okay, but what if instead of a short spacer, we have one that's too long? In that case, the outer races just won't sit properly in the hub. We'll have a tiny gap between the seats and the bearings, and that gap is enough for things to start moving. If there's side loads, there's a good chance that the entire assembly will start moving axially. And if there's room for that, sooner or later the outer races will start spinning as well. If you can picture this happening on a car wheel, I guess you see how this is a safety concern. What we need is a spacer that's correctly sized. One that's long enough to avoid excessive preload, but at the same time does not prevent the races from sitting correctly in their seats. Tolerances depend on the bearing type and application. Nowadays, bearing manufacturers provide fitting instructions for each type and class of bearing, including some online calculators, so always check that first. In the case of my friends, after trying the original spacer, he came to the conclusion it was too short. Then he asked me two new spacers, one with 12mm and a plus 500s. I machined 3 already. I did it off camera as I wasn't going to make a video about them. Come on, they're just spacers. But I'm not happy with them. So I guess that's worth a video. The struggle has been making their faces parallel. Bearings have tight tolerances, and I think it's too easy to inflict uneven loads on the bearings if the spacer is not parallel, at least within the tolerances of the bearing itself. So how bad are my spacers after all? The first one I made was turned, bored, and the first end was faced, all in the same setup. Then I flipped the spacer and used a parallel against the chuck's face to square the part. Finally, I faced the other end and took it to 12mm. So what's the problem? The faces of this spacer are not parallel. They're off by 0.05 of a millimeter. This might have been caused by me kicking the spacer while I was removing the parallel, or more likely due to my chuck's face not being exactly square to the spindle axis. I tried to find the parallelism tolerance for a typical bearing spacer like this, but I couldn't find anything online. I did find an NSK catalog listing up to 3 microns for angular contact bearings, but nothing for ball bearings. Anyway, my gut feeling says 500 is too much, and I'd rather be around 100 or 10 microns. So this spacer looks good, but it's a no-go. For the second spacer, I made the Delrin mandrel. The spacer was turned and bored like the first one, and then mounted on the mandrel to face the first end. Then I flipped it and faced the second face. If I remember correctly, I even machined the first face again, just to ensure I had a proper seating of the spacer against the shoulder of the mandrel. The result was better, and this spacer is off by 300ths. But I didn't like this method much. I had some problems removing the spacer from the mandrel while I tried my best to avoid having it move in the chuck. Eventually, I had to use some pliers and the spacer got some marks. Not a big issue, but also not ideal. Finally, the third spacer. For this one, I used an indicator, knowing the first face was machined square to both OD and ID. I don't see this as a reliable method because the spacer is too short and there's just not enough travel to ensure the part is indicated correctly. Having said that, this was still the best spacer I got, with 0.02 of a millimeter difference in parallelism. But all of this got me thinking, there's gotta be a better way to make this, right? That's when I remembered what I did in the last video with the carburetor bodies. I actually got the flanges very close to parallel with the expansion arbor. Having access to both faces without the need to remove the part from the chuck, that has to be the trick here. I know this wasn't pretty, but sure was fast. So I made 4 of these blanks, 1 for each spacer and 2 extra just in case I missed the dimensions. The 5C collet chuck will probably speed up things at the end, that's why I'm changing. And this is the trick I was referring to. I'm machining both faces without removing the part from the chuck. This way they should come out really parallel. Turns out, I didn't miss the dimensions by much, so I ended up making not 2, but 4 different spacers. And I say by much because, working with microns, I'm fighting temperature here, or should I say thermal expansion. It's not easy. Changing to the 5C did save some time squaring up the spacers to machine the ID, although that's a clearance hole, so it doesn't really need to be squared to the faces. Well, let's measure it. Looks like it's a bit off, something like 5 microns maybe? I think I will stone the faces to clean up any burrs it might have, and then try to measure in a different way. And for that, I got some help from Chronos Limited, which is sponsoring this video. I've been a Chronos customer for a number of years. In fact, a lot of the tools you see me using in the channel came from them, so I'm really happy to have them helping the channel with these tools. This indicator, by the way, is a beast. It reads down to microns, has 50mm of travel, and has a really nice feature that allows to define some target dimension and a tolerance. This way we can check a bunch of parts and quickly find out which ones are out of spec. As for the big box, finally I have some good parallels for my mill. I quickly inspected one of the pairs on the surface plate, and I must say I'm impressed. This is how they average with a 50 millionths indicator. So if you're interested in having a look at Chronos tools, I'm leaving the link to their website in the description. So I'll take advantage of this new indicator to check the height and parallelism of each spacer. Considering the tools I have, I can't think of a better way to make this. Checking if it goes back to 0? It does. Cool. Now I'll draw some lines in the spacer so you can actually see it rotating on the granite plate. So this is the plus 500 spacer. And it looks like I'm 3 microns under the target length. That's not bad at all. And the parallelism is within 2 microns? That's 10 times better than the best of my previous spacers. Okay, let's check another one. This is one of the extra spacers I made. It should have 12.1mm, but it looks like I'm 5 microns over. But the parallelism is still within the same 2 microns. The next one is 12mm, and this one is 7 microns under in terms of length. As for parallelism, this is the worst so far, with 3 microns. Even so, we're still in angular contact bearings territory. I think this is way overkill in terms of precision for a wheel bearing, but it can't hurt to be right. Plus, it's really nice to see you don't need a surface grinder to make this. Let's check the last one. And the last one is 1 micron. 1 micron! That's just awesome. I know I missed the target lengths by a few microns, and that's not really a problem as tolerances exist for a reason, but I'm really impressed with the consistency of the spacers. Even if there's some waste of material, I think the consistency pays off. Before I wrap this up, just a note about bearing types. Today, I focused mainly on ball bearings, but there are other types of bearings. For instance, tapered roller bearings, which are very common nowadays, can be found with or without spacers on most cars. Especially for the cases where no spacer is available, they should be fitted according to their instructions. There's a loading, unloading, and final torque procedure to be followed. I guess what I'm trying to say is, always check the manufacturer's instructions. Always play safe and don't skip the proper procedures when installing safety critical components like wheel bearings. You're not the only one on the road. For now, the only thing left for me to do is apologize to my friend for taking so long to make the spacers. Things are going slow around here at the moment, but the best is yet to come.